So welcome to part 2 of lecture 13. So we just ended off the last part with this big idea that when we're looking at the set of linear maps from V to W, it's the same as studying the set of m by n matrices. So in this part, what I want to do is kind of think about linear maps, the thing objects on the left-hand side, as being viewed as matrix multiplication. So try to translate things back and forth between linear maps and matrix multiplication. So the first thing that we want to do is, given a vector v and a basis v1 through vn for that vector space, we want to associate to a particular vector a matrix. And so the matrix of a vector v is going to be an n by 1 matrix is the matrix mv, and it looks like c1, c2 up to cn, where these CIs are the coefficients of writing V in terms of our basis, right? So where V is equal to C1 times V1 up to Cn times Vn. Now this definition makes sense because this is a basis, so every element can be written uniquely in terms of the basis. And what we're doing here is we're kind of just basically ripping out all the coefficients and putting them into an n by 1 matrix. So this might be a little bit clearer if I do a couple of examples. So in this example, I'm looking at the set of degree 2 polynomials or less. And here's a polynomial, 4 plus 3x plus 17x squared. And I'm going to use the standard basis, which is 1x and x squared. Then the matrix associated to this vector is 4, 3, and 17. All right, and the reason that's true is because we want to really highlight how we're writing our vector v in terms of our basis. So that's our first basis element plus 3 times our second basis element plus 17 times our last basis element. So we're interested in the 4, the 3, and the 17. Okay, one more example here, or two more examples of this. Let's do maybe say a non-standard basis for F2. We could take the vectors 1, 1 and 1, 2, and let's say we take the element 3, 4 in our vector space. Then it's a little bit of work, but you can see that the vector 3, 4, if we write it in terms of this basis, is 2 times the first vector plus 1 times the second vector. So since we've written 3, 4 in terms of this basis, then we have that the matrix associated to this vector is now going to be the 2 and the 1, right? So I'm interested in this 2 and this 1, and that's where those numbers come from. And more generally, okay, if we consider the standard basis, E1 through En of Fn, then for any vector in this vector space, we can write it easily in terms of the standard basis. Then V is equal to A1 times E1 plus A2 times E2 up to AN times En. So now we're thinking of all these AIs as constants. So MV now looks like the vector A1, A2 up to AN. Okay, so we take a vector in Fn, and when we turn it, if we're using the standard basis, we're going to get back the same numbers, but now written in terms of a column. Okay, and I just want to highlight this, right? Because in this course, we view the elements of f of n as rows, right? As I did up in this example here. But now, MV allows us to view elements as columns. Okay, as columns, or more formally, or as n by 1 matrices. Right? And then another thing that what we're really doing here is basically we're making an isomorphism from V to the set Fn, the set of n by 1 matrices, right? So this is all n by 1 matrices, And the map is by taking our vector v and you're mapping it to the matrix associated to that vector, provided that the dimension of your vector space is n. So that's how it works. So we're getting this kind of isomorphism from v to fn, and it's to kind of like take elements viewed as rows, and we then can treat them as columns. Okay. So we'll stop here, and then we'll kind of use this information to talk about linear maps as matrix multiplication.